This video explores the kinetic molecular theory of matter, and the supporting topics would be states of matter, so knowing what a liquid is and what a solid is and what a gas is. The kinetic molecular theory of matter is pretty much a set of statements, and the first statement is that matter is composed of particles with definite sizes and shapes. This shouldn't come as a surprise to us because we've been talking about particles in the forms of atoms and molecules all quarter. What this is saying is, hey, guess what? Those have a definite size and a particular shape. The second statement lets us know that particles are in constant and random motion. So if we have particles, they're moving, unless we are at absolute zero, in which case then, in theory, all molecular motion stops. Because those particles are in constant motion, they have kinetic energy. And kinetic energy comes from the fact that they're in motion. Kind of makes sense when you think about it. Potential energy, on the other hand, is energy that matter possesses because your particles are attracted or repelled to one another. And that's coming from electrostatic interactions, which is a fancy way of saying that plus and minus are attracted to each other, and plus plus or minus minus are repelled. In our third statement, looks like I should do some erasing here, we see that particles possess potential energy because they interact with each other through those attractions and repulsions. So these two statements are letting us know we have energy that are associated with the fact that particles are in motion, and energy that's associated with the fact that some particles like each other and other particles don't like each other. As the temperature goes up, the molecular motion goes up. And because the molecular motion goes up, the kinetic energy increases, because kinetic energy is the energy that's coming from the fact you're in motion. So if you're moving faster, then your kinetic energy is going up as well. Our fifth statement talks about the fact that particles transfer energy from one to another through these collisions. And in this type of collision, which is called an elastic collision, the total kinetic energy stays the same, but it's moved from one particle to another. So it's kind of like if I had $10 and I ran into you, and let's say you were a thief, and you picked my pocket, right? And you managed to get out one of the fives. Let's say I had two fives. And you managed to take out $5, there's still $10. It's just now divided between me and between you. So this statement is saying, hey, this particle and this other particle have different amounts of energy, but when they collide, somebody might give some energy up and somebody might lose some energy, but the total energy that they had from the beginning to the end stays the same. Kinetic energy is considered to be a disruptive force, and that kind of makes sense because we're talking about things in motion, so they're not staying still. Potential energy, on the other hand, that's what's going to potentially bring things together. When particles are attracted to each other, they are going to be more cohesive. And like we discussed, higher temperatures are going to lead to higher kinetic energies, which is going to lead to higher disruptive forces in the system. When we talk about states of matter, we consider that solids have really high cohesive forces and really low disruptive forces. When you think about the solids, particles are really close together, they're in a pretty rigid framework, not a lot of motion going on, very dense. Gases, on the other hand, have very high disruptive forces, a lot of kinetic energy in there, very low cohesive forces. Gas particles are very far apart from one another compared to solids, and so they're not as dense. And when we look at liquids, their cohesive forces and their disruptive forces are about the same magnitude. So when we look at our different states of matter and we compare things like density and compressibility and volume and shape, we know from chapter 1, excuse me, I shouldn't say chapter 1 because we might not have a textbook here. We know from our earlier conversation in the quarter that liquids and solids and gases, we can describe them according to their volume. So let's make this solids, make this liquids, and our final column will be gases. Beep, beep. So density, oops, I just knocked over my microphone. Hopefully that wasn't too loud. Density of solids, pretty high. Liquids, towards the higher end, but kind of in the middle, and gases are low. Compressibilities, gases are very have a very high compressibility. That's why you can squeeze all that air into your car tire. Liquids and solids, pretty low. Volume, solids and liquids end up with fixed volumes or defined volumes, fixed, and gases end up with undefined volumes, which correlates to the compressibility, the fact that you can change the volume by squishing the particles closer together. Shape, we know that solids have a fixed shape, but that liquids have and gases both have undefined shapes. They take the shape of their container.